Dear classmates, welcome back to the last video of the JTech chapter. In the last video, we introduced two mandatory instructions. In this video, we are going to finish the mandatory instruction. Also, we will introduce some optional instruction, and then we will conclude this chapter. In the previous video, we introduced the external test instruction and bypass instruction. There is one more mandatory instruction, which is the sample preload instruction. The instruction of sample preload can be decided by the designer. The sample instruction takes a snapshot of system I/O pins, and the preload instruction controls the value of system I/O pin. So one is observation, the other one is control. So now let's start with the sample instruction. In step 1, we control shift DR to be 0. When we pause a clock DR, we take a snapshot of the system input pin value. And then in step 2, shift DR is changed to 1, and when we clock the clock DR, the content in the capture flip-flop will be shifted out for observation. Please note that during this instruction, mode is always equal to 0, so that the system logic is isolated from this sample instruction. We do not disturb the normal operation of the system logic. And the same thing happens here at the system logic output. We can also capture the value of the system logic output and shift them out for observation. So now, on this tap controller state diagram, suppose that we already load the sample preload instruction. Now we start from the run test idle state. We apply the TMS sequence of 1, 0. At this time, we capture the system I/O pins value, and then one more 0. Then we can keep in this state to scan out the value of observation. And then we can leave this instruction by the sequence of 1, 1, 0. Then we are back to the run test idle state. So for example, suppose we have two chips on this board, and we want to observe the value here. So now, starting from the run test idle state, we apply the TMS sequence of 1, 0, 0, followed by 16 zeros in TMS. At this time, we shift out the contents in the boundary scan cell, and we can observe the values here. After that, we can go back to the run idle state. Now let's look at the preload instruction, which control the system I/O pin by the output flip-flop in the BSC. In the preload instruction, in step 1, shift DR is controlled to 1. When we clock the clock DR, we shift in our test pattern. In step 2, we pause the update DR clock, so we can transfer our test pattern into the output flip-flop. Again, during this instruction, mode is always 0, so that we can isolate this JTAG operation from the system logic. And the same thing happens here. So we can preload the output flip-flop in the output boundary scan cell. Again, on this tap state diagram, starting from the run test idle state, we can apply the TMS sequence of 1, 0, 0, and we shift in our test pattern, followed by 1, 1. At this time, we can update our output flip-flop and 0. So we are back to the run test idle state. Now it's time for you to work on this quiz. Suppose we want to preload chip number 2 by the value 1011. Please fill in the blank in this table starting from the run idle state. Now please pause the video and work on this problem. Okay, have you finished yet? The answer is like this. The TMS sequence is 1, 0, 0, and we shift in 16 bits, of which we have 1, 0, 1, 1 here, and then we leave the preload state by 1, 1, 0. Have you got it correctly? If you look at this TMS sequence, it's actually the same as the sample instruction. Okay, now we finish all the mandatory instruction. We move on to the optional instructions. There are many optional instructions. In this video, we will talk about in-test, which select the boundary scan register and perform an internal test of the system logic. We will also introduce briefly run test, which run the built-in self-test of the system logic, and ID code select the device identification register to identify the device. There are many more optional instructions that can be implemented by the designer. So first, let's introduce the in-test instruction. The purpose is to test the on-chip system logic. So in step 1, shift DR is controlled to 1. When we pause the clock DR, we can load the boundary scan chain. In step 2, when we pause the update DR clock, we can transfer the test pattern to the output flip-flop. In step 3, the test pattern is applied to the system logic, and the output is now available at the output. So shift DR is controlled to 0 again. So when we pause the clock DR, we capture the system logic output in this flip-flop. And then in the final step, shift DR is changed to 1, and when we pause the clock DR, we can shift out the response for observation. Please note that during this process, mode is always equal to 1, so we can test the on-chip system logic. Now let's explain the operation of in-test in this tap state diagram. Suppose that the instruction has been loaded and we start from the run test idle state. We apply the TMS sequence of 1, 0, 0, and by a sequence of zeros to shift in our test pattern, and 1, 1. At this time, we upload the output flip-flop of boundary scan cell, and the 1 again. Then, starting from this state, we perform a capture, and then we shift out the contents in the boundary scan cell. After that, we apply 1, 1, 0, and then we are back to the run test idle state. So now it's time for you to work on this quiz. Given this chip, if we want to apply a test pattern of 1, 0, please fill in the blanks and perform the in test. Now please pause the video and do this exercise. Okay, are you done yet? Starting from the run test idle state, we apply 1, 0, 0, followed by a scan in of 8 bits. At this time, we apply the test pattern 1, 0, and we update the flip-flop and catcher, and then we scan out. At this time, we observe the output of the second flip-flop. The good value should be 0, which is logic low. And then we are back to the run test idle state. Have you got it correctly? Now, the next one is the run bit optional instruction. The purpose is to perform a bit to test the on-chip system logic. As we know, we apply random patterns in building self-test, so we can have random output coming out from the system logic. To avoid the random system logic output, we can do two things. First, we can preload our boundary scan cell so that the boundary scan chain control the output. Alternatively, we can put all the output boundary scan register into high impedance state, as is shown in this figure. This requires a special design in the boundary scan cell, which is not mentioned in this lecture. And the final bit result, either pass or fail, can be left in the boundary scan register or in an internal cell, and it can be shifted out through the boundary scan chain. And the last instruction is Decode instruction. In this instruction, we connect the chip ID register serially between TDI and TDO. Suppose on this board we have 6 chips, and by using the Decode instruction, we can shift out the content in the chip ID code so that we know the ID of these chips. The device ID standard has been set by the JTAG organization. In conclusion, in this video, we introduced the JTAG IEEE 1149.1 standard, which is boundary scan for board level testing. We introduced 4 components. They are tap ports, tap controller, register, and the instruction decoder. We introduced the mandatory instruction, including external test, bypass, sample preload, and we also introduced optional instructions such as in-test, run bits, and Decode. The JTAG area overhead is very small, but it's very useful. So JTAG has been widely adopted by the industry. There are many automatic compilers available to help designers to design JTAG. Thank you for watching the video. Bye bye.